Imagine a universe where tiny particles, invisible to our eyes, determine the fate of galaxies, the structure of elements, and even the very nature of reality. This isn't science fiction, it's basic physics. A field that might seem overwhelming with its complex equations and abstract concepts, but at its core, revolves around simple, foundational principles that govern everything from the smartphone in your hand to the stars in the sky. In this essay, we will embark on a journey through the fundamental concepts of physics without the need for high-level mathematics. Atoms, the building blocks of matter. Atoms are the fundamental building blocks of all matter. Every material substance, from the air we breathe to the stars in the sky, is composed of these tiny particles. Atoms themselves are made up of even smaller components, primarily protons, neutrons, and electrons, which dictate their properties and behaviors. Even ancient civilizations had inklings that matter was made up of invisible particles, deduced from observing natural phenomena. These early theories laid the groundwork for modern atomic theory, which now forms the basis of chemistry and physics. This theory has been universally accepted since the early 20th century and has significantly advanced our understanding of material consistency and properties. The concept that all matter is composed of atoms is fundamental in physics. This understanding helps explain why materials such as copper or oxygen behave the same way regardless of where they are found on Earth. Atoms in their myriad forms construct the diverse universe we inhabit. Protons, neutrons, and atomic number. The heart of an atom is its nucleus, made up of protons and neutrons. These particles are incredibly dense. A teaspoon of them would weigh tons. Protons possess an electrical charge, while neutrons do not, but both contribute equally to the mass of atoms. The number of protons in the nucleus of an atom determines the element's identity, its atomic number. For example, hydrogen, the simplest element, has 1 proton. This distinct count makes each element unique. The atomic number not only identifies the element, but also signifies its properties and how it interacts with other elements. Protons are identical in every atom in the universe, as are neutrons. This uniformity is crucial for the stability of matter and the consistency of chemical reactions across the cosmos. Understanding these particles' roles and behaviors provides a foundation for exploring more complex physical phenomena. Isotopes and atomic weights. While the number of protons in an atom defines its element, the number of neutrons can vary. This variation creates isotopes, different forms of the same element. Isotopes have the same atomic number but different atomic weights due to the additional neutrons. The most common isotope of an element is usually the most stable and abundant in nature. For instance, carbon-12 is the most prevalent isotope of carbon. However, other isotopes like carbon-14 exist and are crucial for techniques such as radiocarbon dating, which helps archaeologists date ancient organic materials. Understanding isotopes is essential for various scientific fields, from environmental science to nuclear medicine. The variation in neutron number affects the physical and chemical properties of elements, influencing everything from biological processes to geological formations. Electrons, the charge carriers. Electrons are subatomic particles with negative electric charges orbiting the nucleus of an atom. They are essential for chemistry, electricity, and overall molecular interaction. Initially, electrons were thought to be embedded within the nucleus. This model evolved over time to a more dynamic depiction, where electrons orbit the nucleus, much like planets around the Sun. Today, we understand that electrons move so rapidly and unpredictably that their exact locations at any given time are indeterminate. Instead, we talk about electron shells or clouds where electrons are likely to be found. These shells dictate an atom's chemical properties and its ability to bond with other atoms. Electrons are significantly lighter than protons or neutrons. Their movement between atoms is the basis for electricity. In materials where electrons move freely, we observe high conductivity, essential for the functioning of various electronic devices. Ions and their influence. An ion is an atom or molecule that has gained or lost one or more electrons, acquiring a net electrical charge. The process of gaining electrons results in a negatively charged ion, while losing electrons results in a positively charged ion. This alteration in electron count can dramatically affect the chemical properties of the atom. Ions are crucial for everything from the functioning of batteries to the processes within our bodies. For instance, the transmission of nerve impulses involves the movement of ions across nerve cell membranes. This movement is also critical in processes like electrolysis and in the functioning of solar cells. In nature, ionization can occur due to high-energy impacts or the presence of strong electric fields. Understanding ions is key to grasping basic electrical principles and the behavior of matter under various conditions. Fundamental forces of physics. Physics identifies 4 fundamental forces which govern the interactions of matter and energy. These are gravity, electromagnetism, strong nuclear force, and weak nuclear force. Each force acts over different ranges and has different strengths, governing the structure and behavior of everything in the universe. Gravity, the most familiar, acts between masses, holding planets in orbit and keeping our feet on the ground. Electromagnetism governs the interaction between charged particles and is responsible for practically all phenomena in daily life except gravity. The nuclear forces act at subatomic levels, holding the nuclei of atoms together or causing them to decay. Understanding these forces provides a framework for exploring a wide range of physical phenomena, from the orbits of galaxies to the fusion processes in stars and the stability of matter itself. Energy, the currency of the universe. Energy is a fundamental concept in physics, representing the capacity to do work. It exists in various forms: kinetic, potential, thermal, chemical, electrical, and more. Energy can be transformed from one form to another, but cannot be created or destroyed, a principle known as the conservation of energy. This principle underpins much of physics, explaining everything from why objects slow down due to friction, where kinetic energy is converted to thermal energy, to how plants convert sunlight into chemical energy through photosynthesis. Energy's omnipresence and its transformations are crucial for understanding both natural phenomena and human-made technology. In the broader universe, energy drives the processes that shape galaxies, stars, and planetary systems, making it a fundamental currency of all physical phenomena. Matter and its states. Matter around us exists in 4 primary states: solid, liquid, gas, and plasma. Each state is characterized by different properties regarding shape and volume. Solids retain shape and volume. Liquids adapt to the shape of their container but maintain volume, and gases neither retain shape nor volume. Transitions between these states, such as melting, freezing, vaporization, and condensation, are influenced by temperature and pressure. These transitions are not merely academic but have practical implications in everything from cooking to industrial processes like distillation and refrigeration. Plasma, the 4th state, consists of highly energized ionized particles and is found naturally in stars, including our Sun. Understanding these states and their transitions helps explain various natural and technological processes, enhancing our control over material properties. Thermodynamics, the heat is on. Thermodynamics is the study of heat, energy, and their transformations. The 3 laws of thermodynamics govern all physical processes and are foundational for fields as diverse as mechanical engineering and quantum physics. These laws help us understand how energy moves within systems and how systems reach thermal equilibrium. The practical applications of thermodynamics are vast, influencing everything from engine design to climate science. It helps engineers maximize the efficiency of machines and informs our understanding of global warming by studying energy flows in the Earth's atmosphere and oceans. Understanding thermodynamics allows us to harness and manipulate energy more effectively, improving technology and our understanding of natural processes. Electromagnetism, more than attraction. Electromagnetism is one of the four fundamental forces of physics, describing how electrically charged particles interact. It encompasses both electric forces, which act between static charges, and magnetic forces, which affect moving charges. The unification of these forces into a single framework was one of the major achievements of 19th century physics. Electromagnetism explains phenomena from the macroscopic down to the microscopic level, from how magnets work to why light bulbs glow. It's fundamental to the operation of devices like generators and electric motors, which are pivotal to modern civilization. The theory of electromagnetism also leads to the concept of electromagnetic waves, which include visible light, radio waves, and X-rays, all essential for daily technology and medical tools. Quantum mechanics, the weird and wonderful. Quantum mechanics is a fundamental theory in physics that provides a description of the physical properties of nature at the scale of atoms and subatomic particles. It introduces concepts that defy classical physics, such as quantization of energy, wave-particle duality, and the uncertainty principle. These concepts are not just theoretical, they have practical applications. For instance, the semiconductor technology that powers our computers and smartphones relies on understanding the quantum behavior of electrons. Quantum mechanics also explains how the sun shines, and even allows for the development of technologies like lasers and MRI machines. Despite its strangeness, quantum mechanics is one of the most tested theories in physics and is essential for the continued advancement of technology and our understanding of the universe. Relativity, when time and space bend. Albert Einstein's theory of relativity revolutionized our understanding of time, space, and gravity. It comes in two forms: special relativity and general relativity. Special relativity introduced the idea that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum is constant, regardless of the speed of the observer or source. General relativity expanded this to include gravity, describing it not as a force, as Newton did, but as a curvature of space-time caused by mass and energy. This has profound implications, from black holes to the expansion of the universe, and is crucial for technologies such as GPS satellites, which need relativity to provide accurate location data. Relativity not only deepens our understanding of the universe, but also challenges our intuitions about the nature of reality. Particle physics, the quest for the smallest. Particle physics is the branch of physics that studies the fundamental constituents of matter and radiation and their interactions. It involves high-energy experiments that smash particles together to break them into even smaller parts, revealing the underlying structure of matter. Discoveries in particle physics have led to identifying quarks, leptons, bosons, and other particles that serve as the building blocks of the universe. The Large Hadron Collider, for example, discovered the Higgs boson, confirming a long-standing theory about how particles acquire mass. The ongoing quest in particle physics pushes the boundaries of human knowledge about the universe, seeking answers to fundamental questions about the origin and stability of matter. The frontiers of physics. As we continue to explore the physical world, new frontiers in physics emerge. These include areas like dark matter and dark energy, which constitute most of the universe's mass-energy content, but remain mysterious. Other frontiers involve the unification of all fundamental forces and the reconciliation of quantum mechanics with general relativity. These challenges not only push the limits of our knowledge and technology, but also lead to new technologies. Understanding quantum entanglement, for instance, is paving the way for quantum computing, which could revolutionize data processing. By exploring these frontiers, physics not only enhances our understanding of the universe, but also drives innovation, shaping the future of technology and our understanding of the cosmos.